And there we are recording. Okay. So the key thing to realize in tonight's lesson is we're going to be comparing two different groups. And in this first case, we're going to be comparing the proportion of kids in one group to the proportion of adults in another. So let's take a look at it. Who owns iPads? That's the name of this question. And it's saying, as part of the Pew Research and American Life project, researchers surveyed a random sample of 800 teens. So N equals 800. And I'm going to call this N1, meaning the first group. And then there was a second random sample. I'm going to use a different color for them. N2, which is 400 young adults. Okay. And it says here, so for the teens, 79% said they own an iPod. So what that means is I can write the following. Now, they're talking about 79% of the people out of this 800. So we label that P with a little hat above it. P hat 1 is 0.79. So quick comment for you. It's called P hat because that means the hat is telling us that it's a sample proportion. So that's what we have there, a sample proportion. Okay, good. And then for the other group, they're saying that for the adults, the young adults, figure was 67%. So we're going to write P hat 2 equals 0.67. So that's what that is. P hat 2 equals 0.67. All right. So that's what we have. Again, that's a second sample proportion. And then here comes the key question. It says here, do the data give convincing evidence of a difference in the proportions of all teens and young adults who would say they own an iPod or MP3 player? Right? So whenever you see those words and statistics, do the data give convincing evidence? That's letting you know that you have to do a significance test. So we need to write our hypotheses first. So let's do that on a new page. Here's what we're going to do. We start off by saying, let P1 equal the true population proportion of teens that own, I'm sorry about that, own an iPod. So I'm assuming you guys know what an iPod is, right? It's like they don't make them anymore, I don't think, right? They just make iPhones. And then P2 is going to be the true proportion, population proportion of young adults that own an iPod. Okay, so because we're comparing two groups, this is called a two sample test. We're comparing two different proportions for two different groups to find out if we think these groups are fundamentally different from each other. Okay, specifically in this case, this kind of problem that we're looking at today is how we state it. We call it a two proportion. Oops, that was a mistake. Sorry. A two proportion z-test. That's what this thing is called. A two proportion z-test. Okay, so HO, our null hypothesis, is going to be that the difference between P1 and P2 is 0. So I'd like you to think about that for a minute. If that's the case, if you have two proportions and their difference is 0, that's really the same thing as saying that the proportions are equal. That's what that's really saying, that P1 has to equal P2. We just write it this way. HA, the alternative hypothesis, is going to be whatever the question wants us to answer. So let's take a look and see what they tell us. Do the data give convincing evidence of a difference in the proportions? So the way this question's worded, they're not saying that the young people, the teens are more likely to have it than the young adults. They're just stating, is there evidence of a difference? So since there's not a direction for this relationship, we're going to write P1 minus P2 does not equal 0. Okay, so that's what's happening there. Any questions or comments so far? Just out of curiosity in this case, which group do you think is more likely to own an iPod? The teenagers or the young adults, right? So you could just think about that for yourself for a minute. And I'm going to say it's probably the case that the proportion of teenagers that own it probably going to be bigger, probably that group. And that's going to be smaller. Is there a question or no? All right, so if that were the case, then I think P1 minus P2 would be greater than 0. Okay, so I think I'm going to do the problem this way. So just have to read carefully about which proportion or which mean they think is going to be bigger, and that will determine the direction of your inequality in your alternative hypothesis. That's a lot of language. So I'll pause for a second. Do you have anything you want to ask me? Again, keep in mind this is being recorded, so you'll be able to review it later and refer back to it. Okay, so once you've done this, it's time to go find the z-test statistic. So we already know that p hat 1 was 0.79, and we know that p hat 2 was 0.67. We know that n1 was 800, and n2, I think, was 400. Let's just make sure I'm reading the question again correctly. Yep, that works. Okay, so now what you're going to do is you're going to find the z-test statistic. So that's going to be our next step. Find the z-score, or what's typically called the z-test statistic. Okay, so it's going to be intimidating looking, and it's going to take us a little bit of time to type in the calculator, but I'll do it all with you and make sure that you feel good about it before we start using the chart. So here's the formula. I'm going to go to a new page. Oh, Andrew got kicked out, which probably what happened there. Okay, so let's go to a new page here, and I'm going to write out the z-test statistics. Here's what it looks like. It's z equals p hat 1 minus p hat 2 over, and here's what you get. You get the square root. Hi, Andrea, welcome back. I think it's you. You get something called, and it looks intimidating, but actually we'll just do it this way. We can say p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 1 minus p hat 2 over n2. Okay, so that looks like a lot. Now, if you think back to the lesson from 2 weeks ago, that denominator looks kind of similar, except there's now 2 terms, right? There's a term for group 1 and then a second term for group 2. And sort of the same thing's happening on top. There's a term for group 2 and there's a term for group 1. So it's sort of like we doubled everything that we did 2 weeks ago. And that's because we're comparing 2 different groups. Okay, so what I'm gonna do now is I'm gonna plug in all the information and we'll see what we got. Ready? So z equals p hat 1, I think was 0.79, I believe. Yep. 0.79 minus 0.67. And then on the bottom, we're going to have the square root of 0.79 times 1 minus 0.79 over 800 plus. This one's going to be 0.67 times 1 minus 0.67 over 400. So that's what we'll have there. Okay. And we just got to go get a z-score and then see what happens. So the top's not so bad. It's like to subtract the top, that's what's that, 0.13. So that's not a big deal. On the bottom, though, we're going to have 2 things to figure out. We're going to have to figure out that term and figure out that term. Then we're going to have to add them. Then we're going to take the square root, that square root symbol. So what I'd like to do is show you, and you could be using all different devices. Some of you might be just using the calculator on your phone or whatever. So I'm going to go to Google and do it there. I'm going to do this first one. I'm going to do this one here. Then I'll go and do this one. Okay, so let's go do this. Ready? Browser, new page, calculator. Here we go. And let's type it in. Ready? So it's 0.79 times, and you can do open parenthesis 1 minus 0.79. Now I should make a comment here. Some of you might not be using a Chrome browser. So I'm using Google Chrome here. So if you type in calculator, you land on this thing that you have. If you're using a different browser, you'll just get a different looking calculator. If you're having an issue where you don't have as many buttons as I have, like I have all these fancy buttons, you can search for a scientific calculator if you want. That might help. So 0.79 is 1 minus 0.79 over 800. I'm going to hit enter on that. And I'm getting this number here, 0.000207. So I'm going to type that in down here, 0.000207. I should have done that in green to match what I had above. So this is 0.000207. Then I'm going to have plus. And now I'm going to do this red term next. So let's go do that. So clear. I have 0.67 times open 1 minus 0.67 closed divided by 400. 0.00055, I think we'll call it that. So this is 0.00055. Okay, doesn't look too terrible. I'm almost there. I just need to get the whole z-score. So that's going to be next. Any questions or comments so far? All right, I think we could type this all in at once. So I think if we're clever, we can do it. Ready? So I'm going to hit clear. And just remember, I want to type in this numerator first, like this. So let me do a little bit of highlighting here. So the yellow goes in first, and then we'll hit the division sign, and then we'll put in this whole bottom. That's what we're going to do. Okay, so that's our plan to get this to work. All right, so let's see. So what do we have? That's a calculator that you probably don't have, so don't worry about that. 0.13 divided by, and then this button over here above, this is a square root button. And I'm going to type the numbers, which I had, 0.000207 and 0.00055. So let's go do that. So 0.000207 plus 0.00055, close parenthesis, enter, and I get 4.73, 4.72 actually. So this z-score is 4.72. So let's pause for a minute. If anyone disagree with anything I typed in or think I have an error or anything else. Okay. So now what you need to do is go draw a picture of this. So we need to remember what z is, and we're going to go draw a picture of what we just computed. So here we go. Here's our normal distribution. Looks like that, right? I'm going to mark off 0 in the middle because that was HO. HO was that the difference in the proportions was 0. HA is that the difference in the proportions is greater than 0. So that's what we have. So we're going to go over here. We're going to mark off the difference in our proportions. It's p hat 1 minus p hat 2, and that was 0.13. And you always have to decide which way to shade. You shade according to whatever HA says. So over here in HA, you'll notice it says greater than. So you're going to shade above like this. Okay. And we just need this area. Okay. So that's going to require that we go to the chart. Don't forget the z-score. The z-score here was z equals 4.72. That's what we got for z. So let's go look at the chart. So let's just AP statistics formula sheet. Here it is. This is one way I type in AP statistics formula sheet to find a chart. I'm looking for a z-score of positive 4.72, and you're going to have a problem here. So let me show you what the issue is going to be. So you'll notice if I look at this chart, on the bottom row, the biggest number I see there, let's take a look what we got. So I'll put this in my notes here. You'll notice the biggest number I see at the bottom is 3.4. And then over here would be like 0.09. So this number, so if I go across and down, that area, which is 0.9998, corresponds to a z-score of 3.49. Now we have a problem. Our z-score, which we got in this question, was 4.72. So that's even bigger than 3.49. So let's remind ourselves what this chart is telling us. So if we look at this information, this is saying that if we have a normal distribution and we go all the way out to 3.49, the area to the left is 0.9998, which means this area here is 0.0002. But our z-score, the one we have, is even further out here. It's over here somewhere. It's at 4.72, which means the area beyond it, this area out here, has to be even less than 0.0002. And that's the best you can say in this question. We don't have an exact area, but we can say that it's definitely less than 0.002. It is literally off the charts. So this area is 0.0002. That's what this is. Okay, so it's extremely small. It's extremely unlikely to observe a difference of 0.13. All right, so let's go write a final sentence then. So we can say, since our p-value of less than 0.0002 is definitely less than alpha equals 0.05, we can reject HO in favor of HA. Okay, so that's what we can say. We can reject HO in favor of HA. And after you write a sentence like that, this is sort of like the cookie cutter sentence that we write at the end of all these problems. You always want to interpret the question in context. So that's what we're going to do next. So let's just do that real quick. So we're going to say, we found strong evidence to suggest that P1 minus P2 is greater than 0, or P1 is greater than P2. Now, I'm saving us a lot of time by writing it this way. Don't forget, P1 is the proportion of teenagers who own an iPod. And P2 is the proportion of young adults that own an iPod. So what we've proven today is that the proportion of teenagers that own an iPod is significantly larger than the proportion of young adults that own an iPod. Okay, so let's pause for a minute. Do you have any questions for me about any of that? I'll make a comment. This is a lot to write down. There's a lot of work here, but you have a video of this problem. So when you go to do a question for your homework assignment 3, you're able to follow these steps. You can replay certain parts of this. Plus, like I said, at the next session 2 weeks from now, I will go over all the details of that question. Okay. There's one more thing we can do actually that you may have heard of in statistics, and it's called a confidence interval. So I just want to briefly show you a confidence interval for this kind of problem. So here's what they look like. They have a crazy looking formula, but they tell us something interesting. So I'd like to show you. You ready? So here's what they look like. It's P1 hat minus P2 hat plus or minus something called Z star square root P1 hat 1 minus P1 hat over N1 plus P hat 2 1 minus P hat 2 over N2. Okay. So you could be posed a question, something like this. Someone could say, find the 95% confidence interval for P1 minus P2 for the difference in proportions. So this looks very intimidating. Let's do the math and see what happens. So P1 minus P2, so that's 0.79 minus 0.67 plus or minus for Z star. I'm going to leave that blank for a second because we'll come back to that, how you get that. And now, luckily, earlier in the problem, when we were back over here, we did the whole standard deviation. So if you look at the denominator thing highlighted in blue, that's exactly the formula that we have in the confidence interval. So what's going to come next is going to be the square root of 0.000207 plus 0.00055. All right, so right now you definitely should be thinking, I'm not sure why we would even do one of these confidence intervals, why we care. They actually turn out to be really practical. So question is, what goes in here? Like, how do we get the number that goes in here, this Z star? And it turns out that's related to the 95%. Related to the 95%. Okay, so how do we do it? Well, there's something called a T-chart. So I'll put this link into Canvas for you for later. But the last chart, these two charts, that's a normal chart, that's a normal chart, and the last chart's called a T-chart. And if you look at the bottom, what you're going to notice is, if you look carefully at the bottom, you're going to see the number 95%. Okay, so that number is right here. There it is. And if you look directly above it, this number 1.96, that number is our Z star. All right, so that's what this chart gives us. It gives us the Z stars, the special Z scores. So I'm going to put 1.96 in here. Okay, so now what I'd like to do is actually find the confidence interval. So this part here is 0.13 plus or minus 1.96. And I'd like to take a minute and figure out what that equals and put that in here. So let's go do that. Here we go, in the calculator. Clear. I'm going to do square root 0.000207 plus 0.00055, close parenthesis, enter, 0.0275. So I'm going to put that back in here, 0.0275. Now, it's one thing that I realize that some of you may not have seen, and that would be this little like plus or minus thing. So that's a way of putting two problems together in one. So let me show you what I mean. One of the numbers here is going to be 0.13 minus 1.96 times 0.0275. And then the other number that you're going to have is 0.13 plus or minus 1.96 times 0.0275. So I just need to take a minute, type these two numbers in, and this question will finish off. So let's go do that. Just looking at everything there. Here we go. So clear 0.13 minus 1.96 times 0.0275. Enter 0.0761. So this is 0.0761, comma, put a little comma here. Is how you write it. You put like a parenthesis and then a comma. And now I'm going to write the other number in a moment. So I need to go type this in. So let's go back to the calculator. Clear 0.13 plus 1.96. Hold on a minute. Just froze for a second. Give it a second there. I'll do it on my other calculator while it's pausing here. So it is 0.13 plus 1.96 times 0.0275. And in that case, I'm getting like 0.1839. So let's see if I can get back to my notes even. This is 0.1, oops, sorry, 0.18. All right, hold on, I have a little bit of a technical issue here. So the number you would have gotten there, if you could just write it down, I'll type it. Maybe it'll let me type it. It's not even letting me do that. Okay, so it glitched out. The other number here would be 0.1839. So, well, it'll work. Hold on a second. Oh, there it is. 0.1. Oh, I'll go this way. 0.1839. Okay, so we did a whole bunch of work. You'd be like, why would I care about this interval? That would be a fair question to say. So our interval goes from 0.076 to 0.18. It was 39. So I'm going to call it 184 when I round it. So what this interval is telling us is the following. We are 95% confident. That's why these things are called confidence intervals. We're 95% confident that the true difference of P1 minus P2 is between those two numbers. We are 95% confident that the true difference of the proportions is between 0.076 and 0.184. So what confidence intervals do is they give us a range of values where we think the true difference in the proportion probably is. What I'd like you to notice is that 0 is not in here. So if 0 is not in here, that means the difference is not likely to be 0. And if the difference is not likely to be 0, that means that these two proportions are not equal. It means that one proportion is bigger than the other. Okay. All right, so that was the first type of problem I want to do with tonight, was the comparison of two proportions from two different groups. I'd like to take a quick 10-minute break. So we'll come back at 7:13. And then at that 10-minute break, we're going to do one new problem, which is comparing two means instead of two proportions. And then we'll be set. The lesson will be done. Okay. So that's what we do. I'm going to stop sharing. Actually, I'm going to pause the recording for a minute. Let's see. Can I do that? Pause it. Yep. Cancel. Cancel that. Now I don't want to stop it. I want to pause it. Okay, so welcome back. We are recording again. And let me just hide the controls here. And we're going to look at a new problem. This time what we're going to do is we're going to look at two groups, and we're going to use statistics to compare the means of two different groups and talk about that. So here's the question. We'll look at this. This is also in your week 7 notes, that link I sent you. Let's take a minute to read this question and then talk about the kind of significance test we're going to do. This problem is titled Paying for College. College financial aid offices expect students to use summer earnings to help pay for college. But how large are these earnings? One university studied this question by asking a random sample of 1,296 students who had summer jobs and how much they earned. The financial aid office separated the responses into two groups based on gender. And here are the data in summary form. So this is an older problem, just so you know. Okay. So let's take a look at it. Sorry about that line that just appeared there. So a couple of things to notice when you look at it, right? You have a group that identified as males, another group that identified as females, and you can see here some information, so like summary information. So let's just make sure we know what all these numbers mean. So that first number N, this number here, is the sample size. So there were 675 males in this study and 621 females in this study. Okay, sorry about my screen jumping there. Oops, that's not what I wanted. Okay, you have to forgive this, the program's just glitching a little bit. This second number is the mean amount of money that that group made. So these are called sample means. Okay, so according to this, the average amount of money made by males in this survey was $1,884.52. And then finally, next to it, these numbers here are the standard deviation of those earnings. So remember what standard deviation measures? It measures the average distance or the typical distance that data points are from the mean. So in this case, the males seem to have a bigger standard deviation, which means they had more variability in earnings. So if you were to speak to males in the study, the different answers you get would be further apart than if you spoke to females in this study. Okay, the males seem to have a higher average than the females in this case. Okay, so what we're going to do now is we're going to do two things. We're going to do a significance test to see if the difference between the male earnings and the female earnings in this study are significant. It seems like it to me. I mean, it's a $500 difference. So you might say that's a pretty big difference on $1,300, but we'll use statistics to answer it. And then we'll also make a confidence interval like we did last time that's designed to capture the true mean difference in earnings, males minus females. So let's go to a new page here and let's start to define some things. We're going to start off by saying let mu1 equal the true mean earnings of males. Sorry about the sloppy handwriting, but my pen doesn't stop working for some reason. Okay, and let's look at the next one. So then mu2 is going to be the true mean earnings of females. Now, let's be clear about statistics, something you should always keep in mind. This problem states that some kind of survey was done and they interviewed around 1,290 something college students. When we're done, whatever we prove here in terms of information, it only applies to groups of people that are like the people we surveyed. So there's always this thing you have to be really careful with statistics, and that is, do you have good data? Like, did you get good data? Is something you always have to worry about. Okay. HO in this case is that the mean difference between the groups is 0. HO is always that. HO is always saying there's no difference between the groups, and that if you see a difference because of your samples, it's just by chance. HA is usually what you as a researcher suspect. So in this case, we probably suspect, based on the data, that males are reporting they're making more money than females. Okay, another thing I should mention here too is that it looks like this was a survey that was handed out asking around sample how much they earned. So these earnings that were given back in the survey are reported by the people. So you never know, maybe somebody lied when they reported this. Okay, so these are our hypotheses, and it starts off just like the other problem. If you think about it, the other question, we started off by comparing two proportions. And when we did that, right, if you look at how it was set up, it's kind of the same thing. HO was that the difference in the proportions were 0, and HA was that the difference in the proportions was positive. And in this case, it makes sense. We think that this is bigger. That's what we think. So that's why we have the greater than symbol. Okay, so the next thing we're going to go and do is a z-test statistic. So we're going to do z equals. Now I should make a quick comment here. I'm using a z-test statistic here today because the sample sizes are so big. There were 675 men in the survey, and I believe there were 621 females in the survey. Those are huge numbers, and when the numbers are that big, you can use the normal distribution. Okay, so here we go. I'm going to write out what this looks like. It's always the first sample mean minus the second sample mean over the square root of the first standard deviation squared over the first sample size plus the second standard deviation squared over the second sample size. This is what your z-test statistic looks like in this case. If you've taken statistics before, you might have heard something called a t-test statistic, like a t-test, which is a very popular test. Once your sample sizes get this large, then you can sort of safely use as normal distribution because the z and the t get so close together you can't even tell them apart. If you had smaller sample sizes, really small sample sizes, you'd have to be way more careful. So we could talk about that maybe another time. All right. Anyway, let's plug in all our information. All the information comes from this chart here. So maybe I'll just put that right here on this page that we already have so I can see it all. So let's see, we're going to have z equals 1884.52 minus 1360.39 over the square root, right, of the first standard deviation, so 1368.37 squared over the first sample size, plus the second standard deviation, 10037.46 squared over the second sample size. And so you can kind of see we're on our way. It's another complicated formula, but we're going to end up with something that looks like z equals. So just for example, on the top, I'll just tell you 1884.52 minus 1306.39. So z equals, what do we have? 524.13. And then on the bottom, it's going to take a little bit longer to type in. So I'm going to go do that in the calculator. So let's go do that together. A lot of numbers there, but I think we can get it. So here we go in the calculator. I'm going to try and type it all at once. So I'm going to do square root. And the first standard deviation, if we remember, was 1368.37. So I'm going to type 1368.37. And I'll press, there's no x squared key, but down here next to 0 is an x to the y key. If you press x to the y 2, now you can see that exponent. Then I'm going to do plus, and then the other number was 10,037.46. So here we go. 10,037.46 x to the y squared. And I hope you realize I forgot to do something. In this problem, I was supposed to divide both of these by the sample size, right? You can see that right here. Divide by 675, divide by 621. So luckily, I can just go back over here and just press on it, I think. Let's see if it'll let me do that. Oh, it's not. So I have to clear a little bit. So I got to go back. Should have divided by 675. Now plus. Sorry about that error. What do we have again? 10,037.46. 10,037.46 x to the y squared divided by 621. Close parenthesis, enter, and we're getting about, what is this, 67.14. So that's our denominator, 67.14. Okay, so let's actually divide these and see what we get. So if I do 524.13 divided by 67.14, I end up getting 7.8. Okay. Now you probably know already that that is a really big z-score. In the previous question, if you remember, we had a z-score that was like in the 4 range. And that was literally off the charts, right? This one's even further off the chart. Just in case there's any doubts, like trying to remember that, let's go back to the Z chart for a second and take a look at it. So back over here, here's our Z chart. Let's make this a little bit smaller. Okay, and what I want to do is get that last line. So here we go. And if we look in here, what we can see is 3.4, and then this column will be 0.09. So if I go down, the number I get, 0.9998, and then Z equals 3.49. So again, if we draw a picture of that, what that means is if we have a normal distribution, over here we have 3.49 equals Z. The area on this side would be 0.9998. So this little bit of area up here is 0.0002. But our z-score that we got is way out here somewhere. It was z equals 7.8. So it's so far off the screen, right, that clearly the area above that has to be less than this 0.002. 0.0002, forgive me. So now we're ready to answer our question. So here we go. We can say the following. We can say, since our p-value of 0.0002 is less than alpha equals 0.05, we can reject HO in favor of HA. So we're going to reject HO. We think HA is true. So that means we have strong evidence to suggest that mu1 minus mu2 is greater than 0. And you'll see, I mean, I sort of love writing something like this last piece. It's so compact. But if you remember, we defined mu1 later before in the question. We wrote down that mu1 was the true mean earnings for males, and that mu2 was the true mean earnings for females. So what we've just said is, wrong sentence there, here it is that we have strong evidence to suggest that mu1 minus mu2 is greater than 0. What we're really saying is that we have strong evidence to suggest that that number is bigger based on this data. Okay. So now, of course, you can be critical of any study. Remember, these people reported what they made to the college, so we don't really know if maybe they were lying or something. It's also possible. Okay. Last thing you could do, you could also find a 95% confidence interval. And if you wanted to do that, it would look like this. X bar 1 minus X bar 2. Ooh, a little bit of mistake there, sorry. X bar 2 plus or minus Z star times square root S1 squared over N1 plus S2 squared over N2. So very familiar, right? It's just like the other one. Okay, so we just need to go get all our numbers and plug them in. So X bar 1, 1884.52. So this is going to be 1884.52 minus X bar 2, 1360.39, 1360.39 plus or minus Z star. Now we already looked that up before. quick reminder, what you do is you go back to that chart, go to the last chart here, and you decide what level of confidence you want. So the question asks for 95%. You should know you have the option to change that, but in this case, they asked for 95, so I'll do it. Here's 95%, and the number right above it is Z equals 1.960. So that's what's going to go in our confidence interval, 1.96 times. And then this crazy thing we already did. We did that before when we did our significance test. So if I just go back to remind you, here's all the math for that. You can see that crazy thing in the denominator. There it is. And it just turned out to be 67.14. So that's what's going to go in our confidence interval, 67.14. Okay, great. That difference between 1884.52 and 1360.39 was, we found that before also, 524.13. So we're just about there. So our interval looks like this, 524.13 plus or minus 1.96 times 67.14. Same thing applies as earlier. This is really two questions in one. So we're going to have a lower bound and an upper bound. I'll do that for you separately here. So we have 524.13 minus 1.96 times 67.14, and we get 392.5. And then over here, if we just switch that to plus, we end up getting 655.7. So we are 95% confident that the true difference in men's salaries minus women's salaries for the summer in this survey is somewhere between $392 and $655. Notice 0 is not in here. That means that mu1 minus mu2 does not equal 0. In this case specifically means it's greater than 0. mu1 minus mu2 is greater than 0 because the difference you're getting, all the differences here between these two numbers are positive. So it's telling us that the mean income for the men is likely higher than the mean income for the women in this particular study. Okay, so that summarizes the two kinds of tests. So you learned tonight was a two proportion Z test in the beginning, how to compare proportions for two different groups. And the second problem, you learned how to compare the means for two different groups. So those were the last two lessons that I really wanted to teach you. Okay.